to Life with David. I'm David, and today I'm continuing with the 24-switch keyboard that I'm developing for the Pico. Last time we integrated the keyboard with an SSD 1306 OLED display, adding the ability to read and write individual bytes of the Pico's static RAM. My ultimate goal is to integrate the keyboard display with an assembly program that operates on a 64K block of the Pico's SRAM. I also want to be able to modify that same block of memory with the keyboard display. This requires relocating programs, transferring execution between programs, two core operations, and importing a binary data file. This time I'm using the RP2040 C++ SDK to bring everything together. So why don't you join me as we execute everything everywhere simultaneously on the Raspberry Pi Pico. Today is all about moving data and programs around in memory, transferring execution between programs, and two core operations. There'll be 5 different files that I'll include in the UF2 file that will load into the Pico. They include a startup C program that will move the programs and data around in memory, start core 1, and transfer program execution between the cores. The integrated keyboard display C program, which was demonstrated in my last video. A PIO program that works with the keyboard display program. An assembly program that will execute out of core 1. Since I'm still working on that program, I'll use a small demo program that blinks the Pico onboard LED. Finally, a 64 kilobyte data file that the assembly program will access. Here's the sequence that I envision to get the whole process started. After startup in the boot select mode, core 0, executing the first stage bootloader, will load in the UF2 package into flash memory that contains, among other things, our 5 program and data files. Core 1 is asleep at this time. After completion of the second stage bootloader, core 0 will begin executing the startup program. At this point, core 0 will wake up core 1, and core 1 will begin executing the keyboard display program. Core 0, still executing the startup program, will copy the assembly program from flash memory to near the bottom of static RAM. Continuing with the startup program, core 0 will copy the 64K data blob from flash to static RAM starting at address 20020000 hex. Finally, the startup program will transfer execution of core 0 from the startup program to the assembly program in static RAM, never to return. In my past bare metal work, I've copied programs and data into static RAM, transferred execution into static RAM, and initiated two core operations. But this time I want to use the Pico SDK. Yeah, I know it might be sacrilegious for me to use the SDK in my bare metal adventures, but I'm using C programs and will eventually want to communicate with the Pico using the USB interface. Since I don't want to waste a year of my life reinventing the wheel, I'll acquiesce and use the SDK. Perhaps I'll even like it. But that means I have to develop some different procedures on how to go forward. So I'll start slow and go step by step as I build a set of skills to reach my final goal. Here's my plan. First, I'll simply use a C program that resides in flash memory to transfer execution to an assembly program that also resides in flash. I will only use core 0. The second step is to use a C program that resides in flash to copy an assembly program that resides in flash into static RAM and then transfer execution to that assembly program in static RAM. I'll still only use core 0. Next, I'll use core 0 to start core 1 using a C program in flash. Core 1 will execute an endless loop within the C program while core 0 copies over an assembly program from flash into static RAM. Core 0 then transfers execution into the assembly program in static RAM. The next step is to do everything we did before, but also transfer in a 64K data blob into flash and then copy it into static RAM. The last step is to accomplish everything we did before, but also transfer execution of core 1 to the keyboard display C program with the associated PIO program instead of simply a loop within the original C program. For this trial, I used my USB to TTL serial adapter that I've used in several previous videos. I introduced it in Bare Metal Adventures 3, and I'll leave a link to that video in the description below. Eventually, I hope to use the Pico's USB interface, but that's for a later time. For all the demonstrations in this video, I'll use the same assembly program, which simply blinks the Pico's onboard LED. It's an adaptation of the program I developed for Bare Metal Adventures Chapter 1. I'll leave a link in the description below. In this case, I changed the preamble to include information to allow the linker to specifically place it in memory. I've assigned it to execute from input section My ASM program. I've also defined the entry point for the program as ASM entry. I declared ASM entry as a global variable so all the other programs know where it is, and then I added it as a label to identify the start point. In addition to the C program, there are two additional files that control how we copy and execute the various programs, the linker script and the CMakeLists file. CMakeLists.txt tells CMake how to create the nmake files script, which in turn tells nmake how to compile and link the various files. The linker script tells the computer where to locate the various files and sections in memory. I'll start with the memmap default linker script that's provided with the C++ SDK and modify it as needed. Let's begin with the simplest case, transferring execution from a C program in Flash to an assembly program in Flash. I'll copy the default linker script into a new file named memmapstaged.ld before I start modifying it. Notice in the memory section that the flash is not hard-coded to a particular size. That's because the RP2040 can have a variety of flash configurations. Here's the equivalent hard-coded statement for the Pico. I've added the input section MyASM program to the output section.txt. This output section resides in Flash. I'll identify two external variables, MyASM program start and MyASM program end. This allows the project to know where the assembly program eventually landed after linking. In between the variables, I'll keep input section MyASM program. This allocates space in Flash for MyASM program even if there's no data. The CMakeLists.txt file for this example is pretty basic. In the Add Executable section, I'll list both the assembly and C programs. Then in the next statement, I'll identify the custom linker script we're using, memmapstaged.ld. I'll also turn on the UART and turn off the USB communications. This makes troubleshooting easier for me. Eventually, I'll implement full USB communications. The C program is also very straightforward. After including various headers, I'll declare several external variables. In this case, the only one I really need is ASM entry. However, I included the other variables in preparation for later examples. In the main function, I'll initialize the RP2040 and then print a message to the UART. I'll define the function entry where a pointer is set with the location of the ASM entry, which points to the start of the assembly program. Because we're working with an ARM Cortex-M0 Plus core, we're in thumb mode, so we need to set the least significant bit when we make a branch to tell the processor to stay in thumb mode. The next statement calls the function entry, which will transfer execution to the assembly program. The tight loop at the end is just a trap in case the transfer to the assembly program fails. Let's try it out. As usual, I'll navigate to the empty build folder within the developer command prompt. Then I'll enter CMake -G nmake makefiles which will populate the makefile. After completion, I'll enter nmake, which will start the compilations and linking. Finally, I'll copy the UF2 file into the Pico. You can see the message prints on putty and the LED starts to blink. That's pretty simple, but let's look at the disassembly and map files to understand where the assembly program lives. In the map file, I search for my ASM program to find the input section. Here we see our two external variables, my ASM program start and my ASM program end. For this example, the starting and ending addresses in Flash for our assembly program are 1000 1B48 and 1000 1BC8 hex respectively. When we go to 1000 1B48 in the disassembly file, we find the entry point into the assembly program ASM entry. The assembly program fills the next 80 hex bytes. Now let's try executing the assembly program out of static RAM. For longer programs, executing out of static RAM is much quicker than using Flash. However, when the power is interrupted, static RAM is erased. Therefore, I want the assembly program to reside in Flash memory until we start the processor. This means we have to build the program to execute out of SRAM, load it into Flash, and then move it into SRAM when we need it. For that, we need to know the beginning of the loaded program in Flash, where it will eventually be located in SRAM, and the length of the program. Let's see how we get there. I'll start by modifying the linker script. Note that RAM starts at 20000000 hex in memory section of the script. Since the linker script is sequential, I'll find the first RAM entry and locate my program to start after that. In this case, I chose to create it after the output section uninitialized data. I created a new output section, RAM text. I'll identify the starting location of the assembly program using the external variable myASMProgramStart. The equals dot tells the linker to remember that address. Note that the external variables can be named anything. You just have to be consistent across your project's programs. Also, an external variable should only appear once in the linker script. Otherwise, the linker could report an unintended address to other programs. Then list the input section you want to reside in that output section. It's good practice to use keep with the input section of my ASM program. This prevents the linker from discarding this section if the section is empty. For more sophisticated programs, an input section might be required even if it is empty. Then I'll memorialize the ending location of the assembly program by using another external variable, myASMProgramEnd equals dot. The next statement tells the linker to compile the program to execute out of RAM, but store it in Flash. The external variable Flash myASMProgramLoad memorializes the loading address of the output section RAM text. This variable, along with the starting and ending variables, gives us everything we need to copy the assembly program from Flash to SRAM. The copying is handled by the C program. After including the needed headers, we declare the three external variables and the assembly program entry point. Then create the void function copyMyASMProgram. Here, the size is calculated by subtracting the program start address from the program end address. Define a pointer DST which points to the address where the assembly program will reside in static RAM. Similarly, define a pointer SRC which points to the start of where the assembly program is loaded in Flash. Then use the memcopy function to copy the file that is size bytes long from SRC to DST. Then return. In the main routine, initialize the Pico and call the copy routine. Then print out the addresses and size of the data that was copied. As in the previous example, create a void function to jump to the entry point of the assembly program with the least significant bit set to stay in thumb mode, and then call that function to branch to the assembly program. The CMakeLists and assembly programs are exactly the same as in the previous example. Let's try it out. As you can see, the program reports that it copied the 76-byte long assembly program from flash starting at 10004360 hex to SRAM starting at 200000C0 hex. We can verify load and start addresses of the program from the map file and the disassembly file. The next example uses both cores of the RP2040 to execute a C program out of flash simultaneously with an assembly program in SRAM. The assembly and linker scripts are the same as in the previous example. In the C program, I'll include a multi-core header to support 2-core operations. I'll add another void function that will serve as the core 1 entry point. This routine prints a message to the terminal every 2 seconds. In main, we initialize the Pico, print a startup message, and then identify which core the C program is currently on. Then the keyword multi-core launch core 1 starts core 1 using the function core 1 entry. Core 1 now just prints out the message every 2 seconds while core 0 continues in main. Like the previous example, core 0 copies the assembly program from flash to SRAM and then branches into the assembly program, never to return. The only change to the CMakeLists file is to add the Pico multi-core library. When we run the demo, we see the output of the terminal at the same time as the LED blinking, demonstrating that both cores are working. The map and disassembly files are nearly identical to the previous examples. The fourth example adds moving a binary data file called a blob from flash into SRAM. This requires modifications to the linker script to slot the data into SRAM and changes the CMakeLists file to convert the blob into an object file. The C program also has to handle moving the blob from flash to SRAM. Let's first take a look at the blob. This is 64 kilobytes of data. The first half of the data is empty, with data starting at 8000 hex. This data will change, so I can't just make an object file offline and copy it. It needs to be compiled each time. Moving to the linker script, I'll modify the memory section to split the static RAM into 2 sections. 128 kilobytes of RAM, which starts at 20000000 hex, where the assembly program will sit, and 128 kilobytes of EMU RAM, which starts at 20020000 hex, where the data will sit. The RAM text output section will remain in the same spot as the previous example, but I'll add the EMU data output section at the end of RAM, just before the Scratch X memory. Remember that the linker script is sequential. The count marches along in flash unless a section is specifically located in another area. We can use this to identify the blob's location in flash before the move to SRAM by setting up a dummy output section just before the EMU data's output section. Here, I'll memorialize the blob's location in flash with the EMU load start external variable, and then tell the linker to keep the dummy output section in flash. In the EMU data output section, I'll memorialize the data start, identify the input section, and memorialize the data end. Finally, I'll tell the linker to put this section into EMU RAM, but store it in flash. In the main C program, I'll add the 3 new external variables needed to copy the blob from flash to SRAM, and I'll create a new void function similar to the program copy function that copies the blob from flash to SRAM. In main, I'll simply call the data copy function after the program copy function is completed. I'll add a message to report the status of the copy function before I branch to the assembly program. In the CMakeLists file, I'll add the commands needed to create the data object file to be included in the UF2 file. Inside the Add Custom Command statement, I'll specify the output as an object file. -I binary specifies that the blob should be treated as a raw binary file. -O ELF32 little arm specifies that the output file should be in the ELF format designed for a 32-bit ARM architecture with little endian byte ordering. -B ARM indicates the architecture of the target, which for the Pico is ARM. This is key to making the whole thing work. Rename section .data equals .emu data renames the default data section where the binary input files typically store their contents to .emu data in the output object file. Then we list the input and output files. The depends statement means that if emu.prog.prg changes, it should be rebuilt. Then we create a custom target that we will add to our dependencies. We'll include the blob as another executable file. And then we'll add the add dependency statement, which means we will build the generate binary data target before we build the rest of the project target. Let's try it out. We see that the terminal output states that the copy function has occurred and both core 0 and 1 are running. From the disassembly file, we can see that the EMU data was located at 100048D4 hex in flash and was moved to 20020000 hex in SRAM. Unfortunately, we're going to have to take it on faith that the data actually moved for this example, but we'll be able to verify it in our last example. Here we bring everything together: our assembly program, the keyboard display programs, and the data file. I'll start by creating a startup C program that will perform the program and data copying, waking up the second core, and transferring execution to the assembly and keyboard display programs. It's very similar to the main C program in the last example, except we've identified the entry point into the keyboard display programs. I'll use the attribute noReturn to signal that execution won't be returning to this program. I renamed the main function in the keyboard display program as main program to eliminate confusion. When we launch Core 1 in main, execution of Core 1 will be transferred to the main program label in the keyboard display program. The rest of the startup program is the same as main.c in the previous example. I changed the name of the main function in the keyboard display program to main program. The rest of the program is the same as outlined in Bare Metal Adventures 15. The other associated files, such as the PIO program and the font header, come along for the ride. The linker script, assembly program, and the data files are the same as in the previous example. The only other change is to update the CMakeLists file to include the new files and additional libraries needed by the keyboard display programs. Let's try it out. After the UF2 file is transferred into the Pico, the onboard LED begins flashing, indicating the assembly program is running on Core 0. Then the SSD1306 display comes to life. We can now use the keyboard display to verify the data has been copied into the proper location. I'll enter 8000 hex and press the Load Memory Address Register button. The data in that location is A0, which matches the data in the data file. I'll press Examine a few more times, and those results also match. I think this qualifies as a resounding success. Thanks for joining me today. This time we did the hard work of getting assembly programs, C programs, data files, PIO programs, and header files to all play nice together. I realized this would be difficult, and it took quite a while to figure out. But now I can move forward toward my ultimate goal of using an assembly program with my custom keyboard and display. Next time I want to pass information between an assembly program and the keyboard display. It might involve interrupts or intercore FIFOs or both. I don't know yet, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!